Alright guys, welcome to school. This is going to be a very fun video. We're starting to get into the meat of calculus, and so today we're going to be studying the derivative meaning. What does it mean? How can we use it? And how can we make things a little bit more relevant into an everyday discussion? So with that little bit of introduction or motivation, let's jump right into our material. Okay, so previously we were looking at how to find the average rate of change for a position function. What are we looking at here? We're obviously looking at a parabola, and this parabola basically models the trajectory of an object, right? If we wanted, since this is the position of the object, this function, this parabolic function, and we want to find the average velocity, well, we simply take the slope between 2 points, right? And so the slope between 2 points basically create a line, which we're going to call the secant line. And how do we approximate that slope? Well, we take point 1, which is expressed here by the expression a f of a. And so that value is 1.5 and 108. All right. And my second point is going to be a horizontal distance of h. H we previously said was going to be called the step, right? And so we evaluate another point, a plus h, right? And that second point is going to be 2.5 and 140. The slope is simply the change in y over the change in x. We know that our step, looking at our graph, is simply going to be 1. Okay, so that's essentially the change in x. And the change in y is 32 feet. Okay, so essentially the average speed between time 1.5 and 2.5 is 32 feet per second. This is definitely not complicated. All we're doing is just taking the slope between 2 points. Okay, so now moving on, if we wanted to find the instantaneous velocity of the object by using this position function, well, we need to find the instantaneous rate of change, and the instantaneous rate of change is essentially our instantaneous velocity. Now, when you find the instantaneous rate of change, you need the slope of the tangent, and the tangent is a line that intersects your function at one point, right? However, in order to find the slope, you need 2 points by definition, right? So what we're going to do is, since we want to find the instantaneous velocity at 2, we want to approximate that tangent by using 2 points that are very, very near to each other, okay? So our slope in this case is going to be this h equals 0.001, okay? So very, very small distance between the points. Okay, so it's important that we emphasize the idea that the instantaneous rate of change is going to be the slope of the tangent. All right, and coincidentally, at 2 or at time equals 2, okay, the instantaneous velocity is 32 feet per second. Okay, this is definitely just a coincidence. And let's keep moving on to our other material. Alright, so just in conclusion, we said that the instantaneous velocity is the slope of the tangent, and we are approximating the slope of the tangent by using 2 points that are very near to each other. More formally, however, in mathematics or in calculus, right, we're going to say that the slope of the tangent is the difference of the function, right, given a step with a limit of h approximating 0. So previously we said that h was 0.01, right? If we wanted to be really, really specific, then we could choose another h that was even smaller, like 0.001, and so on, 0.00001, until you eventually reach 0. And that's when you reach a very specific instantaneous velocity. So in mathematics, we're just going to use this idea, the limit as h, or the step, approaches 0, and that will be the formal definition of the derivative. Okay, how do we read that? We're going to say the tangent slope is the limit as h approaches 0 of f of a plus h minus f of a over h. Okay, now that was a mouthful, but as you'll see, we're gonna put this concept into practice, and it just means we're evaluating the function when h equals 0, or evaluating the slope when h equals 0. All right, this is just a summary, and again, I'm going to provide these notes to you as a PDF file. This is essentially saying what I just told you, that the slope of the secant is the change in y over the change in x, with the change in x being the step, h, okay, and the instantaneous rate of change is the slope of the tangent, with the limit as h approaches or tends to 0, okay? Alright, so let's keep moving on. Alright, now there's something interesting here, right? If we were to look at a position function, this parabola, then we'll see that the instantaneous rate of change right here at A, right? If we look at that slope, we're going to have a positive slope, right? So in terms of position, if your slope is positive, then that means that your position is increasing. Okay, it's increasing, and also the slope is gonna tell you increasing by it's gonna tell you specifically by how much. Okay, by how much. Okay, similarly, if your slope is negative, then your position is going to be decreasing. Okay, and you can just look at this point right here, point C. Okay, and again, by how much, depending on the magnitude of that slope. All right, if a special case, if your slope equals 0, that means your position is neither increasing nor decreasing. Okay, and that's a very important concept in calculus, because when the slope is 0, that means you have reached a max. Okay, or a min. And so the derivative comes in very handy when you want to find out a point in which you optimize a position, or optimize a price, or optimize an investment, or whatever it is that your function models, okay? So that's important to keep in mind. It is one of the key uses of the derivative.